So the electronic double layer is quantified by a number called the zeta potential. Okay, this describes basically it's a unit or a metric rather for comparing double layers to each other. So let's take a closer look at the wall again here. Here it is. And we get a stern layer that comes in nice and close here. And we get a diffuse layer out here that's a little bit more, occupies a little bit more space. So we're going to define 3 places in here. We're going to call this A. We call this is the interface between the stern layer and the diffuse layer. We'll call that B. We're going to call this is the interface between the diffuse layer and the rest of solution, C. Okay, something that you need to know is that anytime we separate charges, in other words, anytime we have a positive charge and a negative charge that are not an intimate ion pair, right, that they're not ionically bonded together, there's an electrical potential. There's a potential energy that wants to bring them together. It's an electrical potential measured in volts. And so what we're going to do is we're going to draw a line like this. I'm going to call this line X because it's about to become our X-axis. And what we're going to do is we're going to plot potential V versus X along that line, right? So here's what that looks like. There's our X line. Here's our potential in volts. And if we did that, we would get a curve that looks something like that until eventually we're basically approaching 0. Out here, every ion has its pair, and so there's very little electrical potential. The closer we get to the wall, the more separated these charges become, we get a little bit more potential. So that's like this. So we can consider the start of this thing position A, that's here. So if we plot that, so here's A. That means that that is some value of potential. We call that the surface potential. Okay. If we go further along this X, we're going to get to this place that is the interface between the stern and diffuse layer. Let's call that B. This gets a name too. That's called the stern potential. And then finally, when we get to position C, maybe I've drawn this a little too stretched out. Maybe position C would be a little further upstream here, but that's okay. Further down on this curve, we get to a potential that we call the zeta. And I am not great at drawing Greek, but I've been practicing zeta for many years. I hope that works. That's the zeta potential. That's the value that we care about. It describes essentially the strength of this electronic double layer. So this brings us then to the actual mechanism, right? The actual mechanism that comes into play in electrophoretic separation techniques. And that mechanism, electroosmosis, or much more commonly referred to as electroosmotic flow, or EOF. So here's what happens in electroosmotic flow. In electroosmotic flow, we have some pore or some tube like the capillary. This can also be like the pore in a spongy hydrogel, for example, a hole in an otherwise monolithic material. It has an electronic double layer. So here's our negative surface potential. Here's the stern layer. Okay, and there's a diffuse layer out here. We said the diffuse layer is held weakly enough that it can move. And so if we apply an outside force, we're going to do that by applying plus voltage and minus voltage, that is some electric field, right, between these 2 points. We are going to see the diffuse layer move, but not the stern layer, of course, because it's held too tightly. We're going to see the diffuse layer move at a velocity that we call V sub EOF, the velocity of electroosmotic flow. And here's the trick to this. When these diffuse layer ions move, right? So the ions move, but they bring with them their hydrating water molecules, H2O, sorry, there we go, H2O. Right, so the ions move, but they are all hydrated by some radius of coordinated water molecules. Well, it turns out those water molecules are coordinated with other water molecules, which are ultimately coordinated with other ions further into solution, into the middle of this capillary, away from the diffuse layer. Those ions are hydrated by other waters, which are coordinated with other ions, etc., etc., etc. The point is that only these belong to the diffuse layer. All of the rest of this is going deeper out into solution, but all of this moves at the EOF because they're all dragging each other along. Basically, our diffuse layer ions move, they drag water at the same velocity, which drags ions at the same velocity, which drags water, which drags ions, etc., until eventually EOF drives the bulk solution, that is all of it, everything stretching from wall to wall, the whole thing moves at velocity EOF. Okay, that's the net result of applying a potential in an environment with an electronic double layer. So let's just finish up this discussion of electroosmotic flow by describing mathematically, or at least quantitatively, how we get to V EOF. So we're going to start from a very similar formulation as we did when we talked about electrophoretic mobility. We're going to define a new mobility we call the EOF mobility times the electric field. So the bigger the field, the faster these things move. But what goes into this mu EOF? Well, we get the permittivity of the vacuum. This is a physical constant of the universe. This is not a property of our system. Times the permittivity of our actual solution that this is happening in. So this is absolutely a property of our system, of our solution specifically, times the zeta potential. That's terrible, but there we go. Times the zeta potential, which is a property not of our solution, but of the combined solution and the wall, right? The solid part of the system, divided by the viscosity. So as the viscosity of this solution goes up, this VEOF goes down. And that makes sense, right? It's more resistance to flow as viscosity goes up. Multiply that times our electric field. So let's just remind you that E sub 0 is the permittivity of the vacuum, a physical constant of the universe. E is the permittivity, sorry, epsilon without the sub-zero, is the permittivity of our solution, which is a property obviously of the solution. And finally zeta, which I'm going to try to do better this time. That's a little better. Zeta is the zeta potential. Okay, so folks, this is where we're going to leave off today. And I'm leaving off here for a very specific reason. This wasn't a lot of lecturing for today. I certainly didn't eat up your full 50 minutes. And you guys are paying me to teach you science for 50 minutes. But I'm stopping here because we are all trapped indoors, or at least partially indoors. And we have a beautiful, beautiful day on our hands out there. So I've been telling all of my friends when I talk to them, hey, make sure you're getting outside and getting some sunshine. And I start these lectures off very often with hello, my friends, but I haven't told you guys this. So today is my day for telling you guys to take the whatever time I've left you, 15, 20 minutes that we didn't lecture that we would have lectured, and just go soak up some sun. Okay, it's going to be good for you. It's going to help wash away those quarantine blues. I'm going to be back on Wednesday, and we're going to start pushing a little closer to seeing these physical mechanisms turn into a separation technique. Take care, everybody.